Let us solve another problem by applying the theorem. So, the recurrence relation given is an equals 2 into an minus 1 plus an minus 2 minus 2 into an minus 3. So, this is the recurrence relation. Now, the given conditions are a0 is 0, a1 is 1 and a2 is 1. This is the initial condition given. So, what appeared just now? R cube minus 2r square minus r plus 2. This is the corresponding characteristic equation for the recurrence relation. Well, do you observe that this has come from the given recurrence relation r cube minus 2r square, because this was c1 there, right? 2 into an minus 1, so c1 is 2 here. An minus 2 has the coefficient as plus 1, therefore it is minus r, and it is minus 2 into an minus 3, and hence it's a plus 2, right? So this is the corresponding characteristic equation. Now, let me write this as r cube minus r square minus 2r plus r plus 2. I'm just expanding minus 2r square and I'm writing minus r as minus 2r plus r. So this is how I'm writing the characteristic equation. Now, what I observe is r square minus r minus 2. If I can take it out common, that is, I've done some jugglery and I've got this r square minus r minus 2 into r minus 1 equals 0. So if you multiply these two polynomials, you will get the given equation, which is r cube minus 2r square minus r plus 2 equals 0. So now, by solving this quadratic equation, we observe that it is r plus 1 into r minus 2 into r minus 1 equals 0. Now, this will give the distinct roots of the characteristic equation, which is r equals 1 minus 1 and 2. So, these are the distinct roots of the characteristic equation. So, now that we have found out the root, we can find out the solution for the recurrence relation. What will it be? An equals alpha 1 into minus 1 to the n plus alpha 2 into 2 to the n plus alpha 3 into 1 to the n. Very simple. In place of x1, x2, x3, I have just substituted minus 1, 2 and 1. Now, this becomes, if I substitute n equals 0, I get it as a0 equals alpha 1 plus alpha 2 plus alpha 3. And if I substitute n as 1, we get it as a1 equals minus alpha 1 plus 2 alpha 2 plus alpha 3. And if I substitute n as 2, I get it as a2 equals alpha 1 plus 4 alpha 2 plus alpha 3. Right? Just substitute 0, 1, 2 in the above equation and you will get these three simultaneous equations. From the given initial conditions, we know that a0 is 0, a1 is 1 and a2 is also 1. Now, solving these three simultaneous equations, right, by whichever method you want, using the method taught by you in the school, you can find out that alpha 1 is 1 by 6, alpha 2 is 1 by 3 and alpha 3 is minus 1 by 2. Now that I have found out what is alpha 1, alpha 2 and alpha 3, I can substitute in this above solution equation and I obtain an as 1 by 6 into minus 1 to the n plus 1 by 3 into 2 to the n minus 1 by 2 into 1 to the n. Right? So, this is the corresponding solution to the recurrence relation.